Welcome to this PyMCon talk on enabling uncertainty quantification from basics to complex models. I am Linus Seelinger. I am postdoc at Karlsruhe Institute of Technology, and this is joint work with Anne Reinertz, who is assistant professor at Durham University. In this talk, I'm going to give a brief introduction to UMBridge, the underlying technology that we use to build UQ applications from basic prototypes all the way to UQ of large simulation codes. And Anne is later going to run a tutorial where we are going to show you how exactly UMBridge works in practice and how you can use it in your own projects. First of all, why do we want to do uncertainty quantification of simulation codes? So think about hurricane simulations. The US National Hurricane Center tells people not to focus on the skinny black line because that's just the most likely path the hurricane is going to take given current best data. In fact, given current best knowledge, the hurricane could take any path within this wide cone. More generally, whenever we have uncertain data, for example, due to measurement errors or incomplete information, we also have uncertainties in resulting predictions based on that data. So especially model-based predictions. In this case, you would see, for example, that the uncertainty of our prediction sort of widens or extends along the prediction over time. That's quite a typical behavior. And you can observe similar behaviors when you try to do inference, where you have an observation of the real world, you have a model of a physical process, and combining the two, you would like to find underlying parameters that are otherwise inaccessible. So summing up, the goal of UQ here is to essentially determine the uncertainties in predictions or inferences as efficiently as possible. So that sounds quite reasonable. After all, what good is any prediction or any inference if you don't have a measure of its certainty, right? Yet in practice, deterministic simulation is much more widespread than uncertainty quantification accompanying it. We believe that one of the main reasons why that's the case is simply technical complexity. Since we now have to combine not only an advanced numerical simulation code, but also advanced UQ methods that need as little simulation runs as possible. And still, even if you combine the most efficient methods from these two fields, you still may have to go to high-performance computing systems, supercomputing, cloud computing, and so on. In order to solve that technical complexity and enable more advanced applications, we introduce the UQ model bridge nicknamed UMBridge. The idea is that we define a universal interface between UQ software and simulation models that is as universal as is math, essentially, and it allows us to couple across programming languages, across arbitrary tools, and so on, which really breaks down the complexity of such UQ applications and helps us a lot in collaborating across fields. In the following, we'll have a bit of a closer look at how this plays out. So first of all, how is it even possible to have this kind of universal interface between UQ and models? As it turns out, in many UQ methods, the simulation model is really just a mathematical function taking a parameter vector onto some kind of a model outcome. And the UQ method is then going to need pointwise evaluations of the model, possibly gradients, Jacobian actions, Hessian actions. Across many UQ methods, this is really all that a model consists of, and therefore one might think that we can really just apply all of these UQ methods to pretty much any model. There are notably some exceptions where UQ methods need additional information about the method, and those UQ methods are a bit more intrusive in the technical sense. Those are not covered by what we show in the following, but really for many UQ applications that interface holds. But despite this rather promising model-agnostic interface, in practice, it really doesn't play out like that. The UQ community, for example, has very different requirements than the numerical simulation community, which leads to different programming languages being used. It also means we can have, due to building complex software stacks now out of UQ and simulation, we can have complex dependencies, conflicts in there. We can have build systems that might not play along. We can have very different approaches to parallelization that don't really align. And last but very much not least, we often need experts from both sides to work together very closely in order to make these applications work, which of course makes those projects all the more challenging. So in order to solve that, and in order to have this sort of abstract mathematical interface in an equally abstract and universal software interface, we take some lessons from microservice architectures. We now say the UQ application is essentially a standalone program, and so is the numerical simulation. We only couple them through a lightweight network-based protocol. It's actually HTTP-based. And so you don't have to implement the protocol yourself. We provide sort of small integrations or adapters per language and also for a number of UQ packages. The interface that these give you mimics exactly what this mathematical interface consists of. Namely, you can do pointwise evaluations of the model, and also you get access to derivative information if the model provides it. What we gain from this is that we can now really link across arbitrary programming languages, since either side really only cares about sending or receiving network packages behind the scenes. On the client side, so in UQ, for example, we have a number of specific integrations into a number of UQ packages. And more generally, we have integrations that are sort of generic for various programming languages. And that holds both for the client and UQ side, but also for the server and model side. So for example, through your bridge, you can now hook up a C++ simulation code to, for example, a MATLAB UQ code without having to specifically adapt either side to that setting. So that makes it a lot easier to just use existing UQ codes and apply them to pretty much any simulation code that you come across. However, we still have the complexity of simulation codes themselves. When it comes to that, thanks to going through a network-based interface, we can now very easily containerize our simulation models. For those unaware, a container is essentially a technology that allows you to package your software along with all of its dependencies and all the data that it needs into essentially a black box that is almost entirely independent of the underlying operating system. In other words, it's fully portable. And we do, for example, publish a container that contains a numerical simulation of a tsunami, which you can now, using the Docker container engine, run with that single command on your system. That single command is going to instruct Docker to download that image that we have published and to run it on your system. And because that container image literally contains both the simulation software, all of its dependencies, and the data that it needs to run, this is really the only instruction that you need in order to make that tsunami simulation run on your system. There's no specific installation procedure on your system happening. And the only assumption on your system is that you have Docker available, which is available for pretty much all modern platforms. So now that with that single line, you have the simulation code running on your system. Requesting a simulation run is pretty straightforward through the Umbridge integrations of various languages and UQ packages. For example, in Python, all that you need is really these two lines. You point Umbridge to where the model is running. Localhost would be your own laptop, for example. And you pass in a parameter vector that the model is going to receive. And the return value of that call is going to be the output of the model for that input value. In case of the tsunami, for example, here we are specifying the source location of the tsunami, and you're going to get back 4 values for water heights and arrival times of the waves at 2 buoys of the coast of Japan. So as you can see, in this procedure, we do not need any deeper understanding of the technical inner workings of that simulation code. This gives us a great deal of separation of concerns because now the simulation expert can handle setting up the simulation code and in fact handle the entire installation procedure and setting up the code to work on a certain data set, for example. Wrap this up in a container and pass that to a, for example, UQ expert. The UQ expert can then just grab this container like so and perform whatever uncertainty quantification on top of it using the UQ tools of their choice. Another benefit from containers is reproducibility, and we make use of that in order to build the first library of UQ benchmarks. So together with a community of more than 15 contributors, we have collected quite a bunch of ready-to-run models and benchmarks, all available as published containers that you can easily run on your system, like the Tsunami I just showed you. And we intend for this to be sort of a common foundation for introducing reproducible UQ benchmarking and performance testing, which I think the community does currently not have, at least certainly not to that degree. Another benefit we get from containerization is that models become also portable to cloud systems. For example, if you want to now scale up a UQ application, let's say you have an advanced UQ algorithm and an advanced simulation code, but you still need computational horsepower, you can use the Kubernetes configuration that we provide as part of Umbridge. Kubernetes is a container orchestrator, for those unaware. Essentially, it's a system that is available on pretty much all public cloud systems, like Google, Amazon, Microsoft, and so on. And it allows us to specify exactly how certain containers are supposed to be run on that system and how they are supposed to interact with each other and with the outside world. The Kubernetes configuration we provide takes an arbitrary Umbridge supporting model container, spins up an arbitrary number of instances of it, and it places a load balancer in front of that model server. That load balancer is now going to take evaluation requests from a UQ client, and it's going to distribute all these requests among the running instances of your simulation code. First of all, this Kubernetes setup is abstract to the point where you can really just plug in a different name for the containerized simulation model that you want to run, and it's going to work for your model. You can just change the number of instances that you want to have and the number of CPUs and memory that you need essentially per model instance, and that's it. Everything else is handled by our setup. Interestingly, to the model, nothing changes because it's really just running inside its container, and each instance just receives evaluation requests through Umbridge as before. To the UQ side, nothing has really changed either, since it's just sending evaluation requests through Umbridge as before. The only thing that's different is that instead of pointing it to localhost for your own system, you point it to the address of where that cluster is running. So you can see that with minimal modification, you can really now move to a cloud system. In order to really exploit the computational horsepower that you get, all that you need is a UQ client that is itself parallelized in some way. And that may be, for example, a thread parallel UQ code written in Python, now offloading thousands of simulation runs to a remote cluster running hundreds of model instances on thousands of processor cores. The entire work of distributing work across the cluster is handled by this Kubernetes setup. So you can really see that with minimal effort, we can take even a lot of existing UQ codes and scale up applications. And we've done that successfully for example, MATLAB UQ codes that have been using MATLAB's parallel for loop in order to parallelize internally. But then we could hook this up to Fortran simulation codes running on hundreds of processor cores on remote systems, for example. All right, so you've seen that there's quite a lot of potential for accelerating workflows from basic setups all the way through benchmarking and large-scale UQ applications on cloud clusters. By the way, support for more traditional HPC systems, so supercomputers, is upcoming in a similar architecture to the cloud architecture I just showed you. It's not quite as abstract because container support is not quite as established, but you gain a lot of the flexibility now on supercomputers as well. All right, finally, let's have a look at how that plays out in practice. So one UQ problem that we've looked at before is this tsunami simulation. The setting that we have is data that comes from two buoys near the coast of Japan. So you see this is Japan. Here we have got two buoys. Those have recorded water heights during the 2011 tsunami. Now, the goal that we have is to perform Bayesian inference in that setting and to find the source location of the tsunami just based on these two time series of water heights. We have an understanding of the physics that happened during this sort of wave propagation of a tsunami, and we've implemented that in the exahype PDE solver. Now all that we need is essentially an efficient UQ method that takes care of solving that. And what we've been using is a multi-level UQ method that takes not only the fully resolved model, but also some much rougher approximations in order to accelerate the UQ problem that we want to solve. Now, in the past, we've successfully done that on a supercomputer running on a couple of thousands of processor cores, combining this advanced simulation code with an advanced multi-level UQ code. So that's quite a success, right? The catch is that it took us weeks and I think even a couple of months to make all the technical issues or to handle all sorts of technical issues showing up along the way, because we had not only incompatible build systems, but also very different approaches to parallelization between the simulation code and the UQ code. We had conflicting dependencies and so on. So there was quite a lot of engineering work going into that. And also quite importantly, you have to handle different discretizations across levels and so on. So there's a lot of complexity that goes into that, and it's unfortunately not the case that we can just take the same application and apply it to a different simulation code or swap out for a different UQ code at that time. However, we went ahead and tried to do the same thing with Umbridge again. In that setting, Anne, who was the expert on the simulation code, could set up the tsunami simulation on her system and do some small-scale testing. Adding Umbridge support, she could use a test script written in an arbitrary language, let's say like Julia, in order to request samples from that simulation code and to make sure that it actually delivers the outputs that we are looking for. Once she was happy with that, she could wrap up the simulation code in a container, which you could now share with the UQ expert in that project, which was Mikkel Lykkegaard, our collaborator on that. He could start testing with a simple UQ code just to make sure that the entire setup is working as he expected. And well, as it turns out, the more simple methods that you might think about when doing Bayesian inference are really not sufficient with this pretty compute-intensive simulation model. So he went to a multi-level method, a different one that we did back then, that he had implemented in his own Python package. In order to make this run with our model, he only has to connect to the model per level and specify to the model on each level what discretization level it is supposed to use. So now we have a C++ simulation code that is wrapped up in a container that Mikkel did not have to install on his system. In fact, he does not need to understand the technical inner workings of this. He only needs to understand how the model behaves mathematically. He could then hook this up to his simulation, to his UQ code written in Python. And there was no specific integration happening to make the two work. All right, after successfully testing the multi-level method, well, we still need some more computational horsepower. So in this project, I took care of setting up a cloud cluster using the Kubernetes configuration that I just briefly mentioned before. Again, since we still only have the Umbridge protocol involved at each stage, that means we had to make no change to the model container itself. And likewise, Mikkel had to make no change to his UQ code. The only change that he had to make is to tell his UQ code to now do 100 parallel requests at the same time, which his code already supported. Mind you, in a parallelization technique that was absolutely not compatible with the MPI-based communication in these simulation models. But again, thanks to Umbridge, this doesn't really matter. All that we need is that this code is able to produce evaluation requests in parallel, and it just works. Finally, in order to make things a bit more fancy, we could still plug a GP emulator in between as sort of an accelerator. But as you can see, this even slots nicely into this sort of microservice architecture. In the end, what you see is a pretty complex setup, but in fact, compared to the weeks and months that we spent before on making that work, this really only took us, I think, a net total of 3 days, simply because working on that simulation model is entirely independent of this large-scale architecture on the cloud cluster. And likewise, we can use an existing UQ code simply because the integration with Umbridge allows it to work with this simulation code despite not being immediately compatible. All right, we could scale this successfully to 2.8 thousand processor cores on a Google Kubernetes engine system. And ultimately, we not only got a pretty good speed up of the UQ application due to a very efficient method, but also development was extremely fast, considering that this is an even more complex workflow than what I described before. Right, finally summing up, UMbridge therefore gives us a single entry point to UQ for simulation developers. And likewise, if you are developing a UQ code, this is a single entry point for you to access pretty much any simulation model out there. All that is needed is a pretty simple integration with Umbridge on either side. This allows you to speed up UQ development from small prototypes all the way to complex applications on supercomputers and cloud computing, as I just showed you before. And it enables us to build the first UQ benchmark library, which I hope will be benefiting the community in the long run. Below here's a link to our documentation as well as to the GitHub repository where we're hosting our code. And I'm looking forward to seeing you at the practical sessions that we'll have after publishing the subsequent tutorial. So thanks a lot for coming and hopefully see you soon.